Have you guys heard of like say like MapReduce, Hadoop, or Spark? No? Okay. So you know that how can you get okay, so you have a tons of work to do. Okay, how can you get things faster? How can you get things done faster? Okay? So one, I mean you can you just speed up, you try to, you work hard and just to get it done earlier, faster. Or you can hire other people, right? Okay? So basically the idea is that you're can you use parallel, right? Can you use more machines to get things more things done? But like parallel computing has like lots of issues though. So like let's see, like like there are lots of machines. This each like square represents like machines, right? Like why do you use multiple machines? I mean, so the when you use multiple machines to do some computation, you are splitting the workload or input across machines, okay? And then the machines will have to communicate to each other, right? Because you cannot just dump all the input on one machine, and then there's no point of using parallel computing. And it turns out that this is really hard for like normal people, like even like most CS major people. Like, parallel computing is really hard. Why? Because you have to synchronize this communication, and then sometimes some machine can die. Like you send a message here, but there's no machine there. Then what happened was that, hey, look, we really want to use more machines, but and although the algorithmic idea is very simple, like handling this some issues, right? It's like annoying issues. It takes so much time. Okay, it requires so much expertise, right? Then like most people, like even most CS majors, cannot do parallel computing properly. Okay, so what's the solution? So like that's why this this kind of framework paradigm appeared. MapReduce, Hadoop, or Spark. I mean, there are some variants. This was developed by Google, and this is some like open source version, and Spark is like some kind of advanced version and so on. But they are like very similar. Okay. And the idea is that okay, maybe using parallel computing you can do lots of very cool things, but maybe we can, but maybe, so okay, so so the question is that can you hide some unknown system issues, okay? But just focus on algorithms or logic, right? That's the idea. Okay, by doing this, maybe we can do. We have to compromise the full power of parallel computing. However, still it'll be useful because again, it'll provide a very easy interface to most programmers. Okay. So initially, like, these were used to for very simple stuff. For example, like hey, you have like some long document, right? And the document has like many different words, and let's just count let's count the frequency of each word. Okay, it's a really easy job, right? But then but such easy jobs, these were developed for such easy jobs initially, and people realized that actually by like tweaking this you can do actually much more interesting thing. Okay? Like intuitively, if you just want to count number of words, right? Hey, what do you do, right? This is kind of so there's some long document, right? Like you split like into like pieces, right? Hey, you just count only. You just only count only some part of the you only handle this sub part, and then it's counting. It's just counting, right? You can just aggregate those counts, right, over more machines. So parallel is the dependency, right, across machines is minimal. So that's easy, right? But however, it turns out that even though there are like more dependencies, right, that you can still do something cool. Okay. So I wrote a tutorial about this, and there are some interesting algorithmic ideas, high level ideas, and I want to cover like a couple of ideas here. Okay, so let's talk about some formal definition here. So, what's so we are going to use the following notation. Uppercase N denotes the input size. Okay, P is number of machines we're going to use, and then M, each machine's memory. Okay, so every machine has some limitation in terms of how much it can store. So initially, input stored across machines arbitrarily. Okay, so if you have visualized this, so this is machine 1, machine 2. M1. So it's machine 1, 2, and P. There are P machines right here. Okay. And the input is like partitioned there. So the union of this input, the partial input will be the whole input. Okay. And what's really special here? So of course, if M is big enough, right? If M is bigger than N, it's super easy, right? Because you can just even one machine is powerful enough to handle the whole input, right? So here the biggest constraint is these are the important constraints. The second is like less important, but the first one is really important. So what does this mean? For some small like epsilon, okay? So the memory of machine's memory is at most n to the 1 minus epsilon. Okay? N is input size. Therefore, it means that you cannot put the whole input on single machine. Okay? So to do computation, you are forced to use more machines, not a single machine. Okay, and then like this one. Let's visualize. I want to put some visual picture here. So it's kind of I would say like this massively parallel. Right, computing. In short, MPC, I'm going to describe it as follows. It's basically like a loosely, like a distributed computing, but it's loosely connected. Okay, So basically, this each individual machine is very powerful, okay? But still, it's not enough to do the whole processing. Therefore, you are forced to use it like in many machines, okay? But like we are not going to synchronize across machines like very often. So like basically, I like this analogy here. So like so it's like think of this like a day and night, and day 2 and night. So the idea is that like let's assume that you guys work alone like in daytime, okay? And you do some work, but you can only work using this like a partial input. You cannot see other inputs here. This is the only data you have access, right? And use some local computation. So this daytime is a local computation, and then I'm just copying these machines, but they are actually the same machine. It's just only for visualization. Okay, at nighttime, communication occurs. You don't work anymore, but it's only for communication. So like okay, so maybe you send out some output, some machine. Again, this is the same machine here. Machine 1, machine same, but I just copied the machines for visualization. And then okay, so this communication occurs. Okay. Now and then the sunrise on day 2 starts. In day 2, again you can only do local computation. Like you have some partial like intermediate or some partial input, and you can only use that data. Okay, and this repeats. And so what's the deal here? Like let's call this like one round. One pair of day and night is a one round. This is round 2. Right? So here the goal is that minimize number of rounds. Okay, that's the goal. We have some computation we want to do, but we want to get this done using minimum number of rounds. So like ideally, we want to use only constant rounds. If not possible, say log n rounds. Very few rounds. Okay. So here, the communication time is the main bottleneck. I mean, of course, we think about the local computation, the running time, but it's communication. The data is so big. That's the point there. Therefore, communication takes too much time. Okay. So to minimize communication, I mean, to be more precise, we want to actually, we want actually to measure how much data we communicate among the machines. Okay. You can do that. But then it's you can actually think about lots of details, but that kind of obscures, hides the interesting ideas. So we'll just try to focus on minimizing the number of rounds, okay, with the ideal goal of being being over 1 rounds or over log n rounds. Make sense? So I want to make some couple of big points here, comparing this model to other computing models. Okay. So a computing model, this is one model. Okay. This is not completely accurate. I mean, it doesn't completely capture the real life, but neither does other models. For example. So far, we thought about, say, what did we do? We thought about a LAM model. LAM means a random access machine, and also streaming algorithms, right? And also, there are some other version called like PRAM. It's basically parallel. Okay, what does a RAM model mean? It's basically this is the most basic computing model we use in algorithmic study. Like if you when you in basic algorithm course, this is the most basic model we use. What does a model? I mean, you can from the name you can infer. It's a random access. So there's a memory. There's a big memory, and then you can access. It is like it's a lot of bits, right? You can access any bit, right? Like arbitrary. You can access this or this. Just you don't have to. There's no, and also there's no limit on the size. That's why it's called a random access machine. You can access any part of the memory arbitrarily, randomly. Okay. Then like what is PRAM? This parallel computing model. This is like very classic model. So I don't want to go into details, but I want to talk about it because I want to once you explain this and maybe perhaps you'll more appreciate why this model is interesting. So PRAM is basically we assume that there's a huge memory. Okay? And there are like some CPUs. CPU 1, 2, 3, and so on. Okay? And like this CPU, it doesn't have its own memory. Okay? So like it does like a very simple computation, and then it stores and reads. Okay? But it's completely synchronized. So it comes to local computation, and it stores and loads. Okay. And what's the problem here? Because the CPU, I mean, this we assume that this has it doesn't have its own memory. Like it's a very like simple. Therefore, it can do very limited computation. Okay. Therefore, it has to access the machine a lot. And then synchronize, and then means that you have to use many CPUs. Okay, but synchronization is very hard. It's not an easy problem. Okay. So like although so like even here like number of CPUs, right? Number of CPUs can be even bigger than input size. It makes no sense in real life. Okay, I mean, just maybe you can have like 100, like thousands. Even in supercomputers, you cannot really imagine that number of CPUs is more than n. Okay, and like complete synchronization in every round, it's essentially impossible. Okay. Although it's nice that because it kind of gives you the idea that hey, how is like design parallel algorithms, still it's very challenging. So here, unlikely in this model, here the machines are loosely connected. So each machine is still very powerful. It has enough. It has a lot of memory. It can do lots of interesting computation. However, it still needs to communicate with other machines because it cannot store the whole. It cannot see the whole input. Okay. Also, let's compare this to like streaming model. So like streaming model, these are the streaming algorithms, and this MPC. These are not completely comparable because I mean there are pros and like streaming algorithms are in some sense more challenging because you can read data in only one direction, right? However, sometimes it's easier because anyway. You have a machine, you can see the whole data, right? But if you look at if you think about like one machine here, it has a limited memory, right? So like so say like I1 prime, okay, so and then the next time I1 double prime and so on. So if you run the whole thing like in over one rounds, then if you focus on machine, you cannot even see the entire input. Because you see, I mean, remember that its memory size is like n to the 1 minus epsilon. It's much smaller than, still much smaller than the input size. So like, okay, it is some part of input in round 1, another part of input in round 2, but still you can never see the whole input unless you use like n to the epsilon like rounds, which we don't want. Okay? So still like you know, these are, you cannot really translate streaming algorithms into this MPC algorithms or the other way. Although sometimes you can, but there's no like some like, you know, black box way that you can play. Okay. And also, I want to also talk about this BSP briefly. This is a pretty old model. Like it was developed, I think, almost 30 years ago. It is like about like 10 parameters. In a nutshell, MPC is a special case of a BSP paradigm. But the problem is that when you have like 10 parameters, right, it's extremely hard to optimize it. Like what do you want to focus on, right? Then when you have lots of things to consider, then it kind of obscures the key ideas. Okay, so in this simple model, by focusing on the minimizing the number of rounds, we'll try to see, okay, what is really challenge here? How can you overcome that? Hoping that we can develop new algorithmic ideas. Of course, you'll have to, you know, adapt the ideas, you know, some engineering tuning, but still, we hope that we can get we can discover new ideas. Okay, that's why we define this model. Not because it's perfect, but it's a very simple way to look at this, you know, these problems, right? Large data problems from a different perspective. Any questions about this? Okay, good. It was kind of some simple like introduction. Okay, so I want to cover I guess I can do this part. So I want to start with the warm-up example. Okay, it's very similar to what is studied in streaming algorithms, but here, unlike in what it did in streaming algorithms, we actually want to count the frequency of every word. Okay, not just the number of distinct elements. It's a different thing. Okay. So what do we do? I mean, I'll be a bit sloppy here because I mean the idea is very simple, but I hope that you can understand what you're doing here. Here's an example. So what is the problem here? So we have like some we have a collection of tuples here. Okay, so this is a label of document. Okay, and W1 is basically a sequence, set over sequence of words. Okay, so example can be, hey, like I say, like a 0, comma, like a data big, right? It means that this document 0 has 2 words, right? Data and big. Okay, so we have lots of such documents. Okay, we want to count how many times each word appears across all these documents. Okay, very simple, like trivial problem, right? If you just use a single machine, you just scan like all these words and you just count them, right? Super easy. So what do we do? So recall that n is the total number of words. So n is the input size. Like here, roughly speaking, it's a total number of words. Okay. So what do you do? Okay, so let's assume that, for simplicity, let's assume that P is each document as at most secured n words. I'm dropping all notation here, okay, for simplicity. So you call that P is, P is not the memory size, it's number of washes. Number of washes. Okay, let's make this 3 assumptions, right? Just to simplify, to illustrate the idea. Okay, so what do we do? I'll be slow here because it's first example. Round 1. So each machine I computes CWI. So can you remember that, so I just visualize this way. So initially, every machine has some partial data, right? They are stored across machines arbitrarily. So each machine I just computes it, count each word's frequency. It's super easy, right? It's like, anyone can do that. Okay, that's what you do in your daytime. Okay, and what do you do in the nighttime? So what do we do here? Let's use that with some hash function, okay? So what did you do here? So this guy, this machine I, compute this way, CW1, 1I, CW2I, right? And most it's CW squared N I, right? Because you assume that there are most squared N different words. Okay, so we're going to use some hash function, say M here, or H. Okay, here is H. And it doesn't matter. So it's a hash function. So we are going to map each word to specific machine. Okay, maybe this W1 goes to this, like W2 goes to this. and W3, this goes somewhere and so on, right? So that's what I do. We communicate this count to the machine designated to for this word counting W. Okay? So by using hash function, each word count will be accounted to specific machine. Okay? So because you use the same hash function, like for example, like hey, like say CW1 I assume it's W1, right? CW1 2 1, CW3 1, like this machine will always work on its own input, right? Then because we use the same hash function, right? W1 will be handled by this machine, right? And then okay, it's not easy, right? Because now each machine, right? Each machine gets a frequency for for the words it's responsible for from all the machines, right? It's around 2. Super simple, right? It cannot be simple, right? And there's like 2 examples. As first example, you're gonna see when you read the tutorial on actual like map reducer. Okay. Any questions about this? So obviously it's 2 rounds algorithm, right? Okay, and then also let's see. So when you think about 2 things here, the number of rounds is of course is 2. That's great, and we also need to ensure that we don't we are subject to memory constraint. Okay, so namely we need to check that. It's round again. Each machine sends, receives up to in this case script n, right? So this is okay because see, I mean if you think about this, right? This input machine 1 like sends the part of input like to the other machines, right? So it's easy to see that this machine does not send more than security n bits. Okay, because I1 size was already less than security n. So this only counters, right? So the total number of bits, right, to represent this will be less than security n. So then these are the only data that this machine sends out. So yes, each machine, round 1, each machine sends out at most security n bits. Likewise, if you look at this one, right, this guy receives from at most security n machines, right? Okay, and assuming that all these words are distributed equally, according to hash function, I'm just making I'm simplifying assumption here. Then it'll get only security n bits. So we are satisfying the memory constraints. Okay, so again 2 things here. So number of rounds, and then we need to ensure that we satisfy the memory constraints. It's good? Okay, it's pretty easy, right? So, okay, now given that we are done with the simple warm-up example, let's move to more complicated algorithms. You'll never really remember this word core sets, but let's remember this partitioning. Okay. So what do we do here? Like okay, the input is so big, so therefore we have to use multiple machines, and we're going to put them, on multiple machines. So the idea is that it's really similar to divide and conquer algorithm. Okay, so we run some algorithm on each machine, and then we aggregate the results and then run the same algorithm again. Okay, so here is some like a meta algorithm. So this is just some of your algorithm A, some algorithm B, some algorithm. Okay, this is an algorithm you can use on single machine. Okay, this X is the input. This algorithm for single machine. Okay, so what do we do? Right, we split the input into multiple pieces, right? So because we have P machines, we are going to partition the input into P sub-inputs. Okay, for each sub-input, right? For each machine I, okay, we run the single machine algorithm on the partial input and let yi be the outcome. It's a very simple meta algorithm, right? So like here the assumption is that yi, the output is smaller than the input size. Okay? So I'm going to start with a very simple example, like extremely simple example, and then like more like interesting examples. This is not in the tutorial. This is not even in the tutorial because it's such simple. But it's just for illustration. I think it's a great example. As well. Okay. So say X is a set of suppose the input is a set of integers. Okay. And our goal is to